of Introduction to Machine Learning. Today we will look at estimating the probability density of a given sample and then resampling from that sample to generate new samples. So the learning objectives are: we should be able to list the applications of density estimation and sampling. We should be able to estimate the sufficient statistics of some distributions, and we should be able to test the goodness of fit of certain distributions, and write the expectation maximization algorithm for mixture of Gaussians, and fit a kernel density estimator on a given set of samples, and also generate samples using Monte Carlo methods or Markov chain Monte Carlo methods from a given distribution. So the first question that comes to mind is, why estimate the density of a given set of samples? So let's say we are given a bunch of data points. So let's take a two-dimensional space, for example. So let's say this is an x1, x2 space, and all we are given is some distribution or some set of samples here, right? So question is, why even try to estimate the density of the samples in this distribution? The first application that comes to mind is that we can perform basic statistical tests, such as what is the mean of the sample, what is the variance or covariance of the sample, what is the, if it is a single dimensional sample, right? So if it is only x1 and we are given bunch of points, then what is the standard deviation, what is the skew, what is the kurtosis, those kind of things, what is the minimum and the maximum, etc. The second question could be that, can we identify outliers? So let's say most of the samples are here, but there is one sample here which here visually looks like an outlier, but can we statistically show that it is an outlier? Then we want to use Bayesian methods. In those cases, we may want to use a density estimation. So for example, if we are building a Bayesian classifier where we want to make a decision based on P of class 1 times P of x given class 1, right? So then this particular estimate could come from a probability density estimation, okay? And then finally, generate new samples. So given a bunch of samples here, can we generate new samples for various reasons? We may want to augment the data. We may want to create an extra set of samples so that we have a larger sample to fit the data on. We may want to create new samples that do not violate the copyright of the existing samples but generate plausible new samples, for example deep fakes and so forth. So these are all good reasons for why we might want to generate samples from a given set of training samples. So the easiest way to do density estimation is to do parametric density estimation. What that means is, we assume that the underlying distribution is a distribution of a known kind with a certain set of parameters, and then all we need to do is estimate those parameters. So the complete way of looking at it would be that we would first visualize the data, then we will shortlist candidate distributions, then we will estimate the distribution parameters, and then we will check the fit or the likelihood of that distribution. So let's take an example. So let's say we are given a single variable, okay, and it is basically and these are the samples of the distribution, the crosses that I have marked. So, and we see that there is nothing outside of on this side, there is nothing outside on this side, and looks like there is no particular region here where the data is more dense versus less dense. So most likely this is going to be a uniform distribution. On the other hand, so what is the y-axis here? Sorry, the y-axis is going to be p of x if x-axis is x. On the other hand, if we are given another set of samples and looks like there are several samples close to a particular value and then less and less samples as we go further away from that value, then most likely this is going to be a Gaussian distribution. So once we visualize the data, we know what are some candidate distributions. If we have a distribution that is skewed towards one side, then Gaussian may not be the right choice, even though we have So let's say there is nothing on this side, but like everything. So let's say we have a bunch of points here, but then they go sparser and sparser as I go towards the right, but there's nothing on the left. So this could be an exponential distribution, for example. So once we visualize the data, and this could be in multiple dimensions also, we get a sense for what are some of the candidate distributions for this particular data. So we shortlist those distributions. Then we estimate the parameters of those distributions, which I will come to in a short bit. And then we will check, comparing two different distributions, which one is the better fit. There is no such thing as the optimal fit. There's only better fits and not so good fits. We can only compare distributions. So that's what we will look at shortly. So what is so how do we estimate the parameters of a distribution? One of the ways of doing that is to look at sufficient statistic. So what is sufficient statistic? Basically, these are a set of numbers that if we find these set of numbers, these numbers will maximize the likelihood of fitting on the data of that particular family of distributions. So let's talk about a family of distributions. So let's say we are looking at Gaussian distributions, right? So the Gaussian distribution in one dimension is described by a mu and a sigma. Okay, so the mu is the center of the distribution, or the 50th percentile of the distribution, and sigma tells us how wide is the distribution. So for example, we could have a mu here, and then we could have a distribution like this, or we could have a mu somewhere else, and we could have a distribution like this. Both are Gaussian, but they have different mu's and sigmas. Okay. So there are certain distributions where if you estimate certain statistics of those distributions, you will be able to find the parameters, the maximum likelihood parameters of those distributions. So let's look at what those statistics mean. So what is a statistic? First of all, it's a descriptor of the distribution. So examples of statistics could be the mean, the variance, okay, min, max, etc. So anytime you take the distribution and you reduce it to one number, that is a statistic of that number. Okay, and that one number is a descriptor. So it could also be, let's say, min and max combined. It could be a range also. So if you reduce it to a few set of numbers, those are the statistics of that number. So this is, for example, expected value of x. This is expected value of x minus expected value of x whole squared. Etc. Right? So and then you have the min and the max. So once we can find certain statistics of certain descriptors of certain family of distributions, then we will be able to find the maximum likelihood parameters that will best explain the data. So in this particular case, for example, you may have a mu1 and a sigma1, and then you may have a mu2 and a sigma2. So between these two, one of these will be a better choice for a given set of samples. Which one is a better choice? Let's see how we can find that. So as you know, the formula for Gaussian distribution is what is given here, and in high dimensional, in more than one dimension, it is given here, where the C is the covariance matrix, okay, and mu is a vector, and x is also a vector. Here x is a scalar, mu is a scalar, and sigma is the variance of the data, and that is also a scalar. This is for one dimension. And this is the expected value of x is mu, and expected value of the square of difference from the mean is the variance. So here, how do we fit a Gaussian distribution? So basically, let's say we are given a bunch of points. So this is your axis, and we are given a bunch of points. Okay. So for this bunch of points, let's call them xi. Okay. So there is something called a sample mean. So sample mean, let's call it mu hat, is going to be simply sum of xi divided by n. N is the total number of samples. So I runs from 1 to n. Okay, so that is a sample mean. This is sample mean. Similarly, we can have sample variance, and depending on whether you want a biased or an unbiased estimator of the variance, we will take xi minus mu hat. Okay, we will sum this over I, the square of this, we will sum it over I, and then we might divide it by n or n minus 1. Okay, depending on whether we want the bias estimate or unbiased estimate. So that will basically be the sigma hat square. So it turns out that for a Gaussian distribution, basically when we want to find a maximum likelihood estimator, then what we simply do is we set mu to be mu hat and we set sigma to be sigma hat. Okay, that's all we need to do. So basically we take the sample, and for the sample we compute the sample mean, and assume that the Gaussian has the same mean, and for the sample we compute the variance and we assume that the Gaussian also has the same variance. So what I will do is I will put a star here, because if I put a star, that means these are optimal in some sense. It's a notation that we often use by putting a star. And if we use any other mu2 and sigma 2, okay, the likelihood of the given data is going to be lower than if we use sigma star and mu star. Okay, so these are going to be optimal in the sense of optimal for maximizing data likelihood. So these are something called sufficient statistic, that if we just estimate these statistics, we know pretty much everything about the distribution, and we know the best fitting distribution for the given data. So this idea of sufficient statistic is only applicable to certain types of distribution, not for every distribution. Some other examples where these are applicable is a is an exponential distribution. As you know, an exponential distribution is going to be 0 when x is less than 0. Okay, and it is going to be lambda times e to the power minus lambda x if x is greater than or equal to 0. So it looks like either this or it looks like this, and so forth. And just to remind you, the area under all of these is going to be 1, because these are probability density functions. So here, if we just find the sample mean, which is expected value of x, if we just find mu hat, okay, what we can say is that lambda is equal to 1 over mu hat. That's it. So just finding the sample mean is a sufficient statistic, and that will give us a best possible estimate or maximum likelihood estimate for an exponential distribution. But here we have to first visualize and see that there is nothing here. There are no samples in the negative range. The samples are more concentrated toward 0 and sparsely concentrated as we go further away from 0. Only then it is a exponential distribution is a likely candidate. Out of all possible exponential distributions with different lambdas, the best fitting distribution is the one that is given by this 1 by mu hat. Similarly, we can look at uniform distribution. If we see a bunch of sample points that are almost uniformly distributed between two extremes, and there's nothing outside those extremes, then basically the uniform distribution itself is given by 1 over b minus a, where b is the upper limit and a is the lower limit. Okay, and outside of that it is 0, else 0. Okay, so here the estimate for b and a is simply, for b it is going to be max over xi, and for a it is going to be min over ai. So if we perturb a and we make it slightly larger, we are going to miss the lowest, over xi. If we perturb A and we make it slightly larger than min of xi, then that min of xi will be 0 according to the distribution, and consequently with the IID assumption everything is going to be 0. So what is the likelihood of the data? So the likelihood of the data is product over I. Okay, so whatever is the distribution f, or let's say whatever p theta of xi. Okay, and the log likelihood is going to be sum over I log of p theta of xi. Okay, so what we want to do is we want to maximize either this or this. Maximize. We want to find a theta. Theta is the parameter. So theta is mu or sigma in case of Gaussian. It is lambda in case of exponential. It is a and b in case of uniform distribution. We want to find the theta that will maximize the product of all individual probabilities. Where this comes from is from the IID distribution, independently identically distributed. Independence leads to the product, identical leads to reuse of the same probability density function inside the product, and if we take log we will get the log likelihood. So this is what we want to maximize, and what we have looked at the sufficient statistics in the last 3 slides. These are the ones that will maximize the likelihood for this particular family of functions such as uniform for a given data set. So now let's say we can find the best fitting Gaussian and we can find the best fitting uniform distribution on the same sample. Between these two, which one is better? So a simple answer is that we just compare their likelihood. So if we take the likelihood of P, let's say Gaussian, right? So let's talk N. Okay, this is the normal distribution of X, and the parameters are mu star and sigma star. Okay. If we take this and we compare it against the another distribution, which could be, let's say, uniform distribution, and this distribution is again over semicolon xi semicolon, and here we have a and b. So between these two, the one that gives us the higher value is going to be the better distribution. Okay. We can also take log on both sides and compare the sum of logs of the probability. So the log likelihood is usually a better used formula, because when we take the product we can get increasingly lower values, and they all multiply and they fall below the floating point limit of a computer. So we several times just use the log likelihood instead. So, but given any data sample, so let's say we are given a few data samples, the actual best fitting distribution is something called the empirical distribution function. What is the empirical distribution function? That I basically put a Dirac delta function, okay, at every sample point and divided by n. So this is Dirac delta function, delta of x minus xi divided by n. So what that means is that my cumulative distribution function will have these jumps of 1 by n at each sample point. Right, so this jump is always 1 by n. I didn't draw it very well, but all of these are 1 by n. So it starts at 0 at the minimum and it reaches 1 at the maximum. So the problem with just using the empirical distribution function as an estimate of all the other points is because we assume that the samples were actually drawn from an underlying, not a discrete like a probability mass function kind of thing, but from a continuous distribution. Just that we didn't have sufficient samples to sample from the gaps between the two jumps. So these samples did not appear just because we had a finite number of samples. So if we take the empirical distribution function, it will fit perfectly on the training data, but it will not explain the gaps between the training data. and that is very crucial. That's why empirical distribution function is not very useful. What is more useful is to approximate this empirical distribution function. So let's say if this is the cumulative distribution function of the empirical data, then we want to approximate it using some smooth curve. So this is some smooth curve that also goes from 0 to 1, and that smooth curve will be different for uniform distribution. For uniform distribution, it's going to be a ramp. For Gaussian distribution curve, it will be a smooth S-shaped curve, etc. So we are trying to use a good approximation to this step type function, okay. And that will basically explain all the missing points also. And if we want to be more rigorous about it, we can also do something like so if we take the empirical distribution function but we fit it only on a subset of samples, it will give zero probability on the samples on which we did not fit it, whereas a Gaussian distribution or a uniform distribution will probably still be able to give some probability, some likelihood on the points on which it was not fit. We held it out just as a validation. So that is also something that we can do to compare two different distributions. One way to find a goodness of a particular distribution is to do something called a QQ plot. QQ plot means quantile plot. So we take the x-axis and we look at the quantiles of an actual distribution, of a theoretical distribution, sorry. And then we look at the quantiles of the actual distribution of the data, and we see whether they form a straight line or not. So what that means is, let's say we are looking at 1 percentile, okay, 2 percentile, okay, and all the way up to 99th percentile, okay, and then we form a table, okay. So this is theoretical Gaussian, and this would be, let's say, sorry, the header here. So this is theoretical Gaussian, and this is practical data point. So let's say this gives us a value of minus 3.6, minus 3.2, etc., and this gives us a value of 2.4. Or standard normal Gaussian would be symmetric, then let's say it's something like 3.6. And here we plot the actual values from the data. So if we have 1,000,000 data points, we can find this would be the 10,000th data point, and that is, let's say, minus 3.4, minus 3.1, and then let's say here it only reaches up to 2.7, right? So if we plot these two, we'll get some kind of a plot, and if that plot is on a 45-degree line, then there's a perfect fit. If the line is slightly changed, it is not at 45 degree, it is sloping, or its intercept is not at 0, then that the only thing that means is that the practical distribution is a normal distribution, except that it doesn't have a zero mean and it doesn't have a unit variance. That could be the difference between the two. So that's all that we need to do to make sure that it looks like. So this is one of the visualization techniques to see whether it is a good fit for a Gaussian distribution. And this need not be just Gaussian distribution. We can replace this with exponential distribution. We can replace this with a Weibull distribution, etc. So that is another way of visualizing the difference between two different distributions, and the more rigorous way is to actually look at the likelihood of the data sample.